Going live, going live. We're live. Woohoo! Hello and welcome to Practicalli. Thank you very much for joining me. My name is John Stevenson, and today we're going to continue with the with the Brave Clojure redux that we're working on. So we're going through the Brave Clojure book just to kind of go through some of the code, maybe update a few things with the tooling that we can do. Just a nice way to kind of practice our Clojure as well. So today we're going to look at writing functions, doing a bit of destructuring, and mainly looking at the differences between loop recur, recursive functions, and things like reduce and reducing functions. So as usual, practically lots of stuff on the website, all the videos there, and the books, and you can contact me via these channels and spot me by these other channels. And thanks to everybody who's already spotted me and keeps me going, especially Cognitech for their generous contributions. And let's see. So we're going to look at do things. We're going to look at this Shires Next Top Model part of the book. So this is in chapter 3, Brave Clojure. The link's in the chat, along with the link to the source code, which is here. And so you can go into Practicalli and look at exercise Shires Next Top Model. And this is all the code we're going to cover today. What's that? Oh yes. I was originally going to go and cover the destructuring aspect stuff, but I've already covered that in Practicalli Clojure 12 as kind of an hour-long kind of video of lots of different aspects to destructuring, both positional and associative destructuring as well. So if you want to delve deeper into that, then that's a good video to watch. So we'll get on with the book. If you've got any questions, please put them in the chat and I'll try and answer them as we go along. Let's get going. So this is an example. It's again, these examples are quirky. They're meant to kind of help you like retain and stick the ideas that it's trying to cover in there. So if you don't know what hobbits are, then don't worry. Essentially what we're trying to do is model hobbits, and for some reason we're modeling how easy it is to hit certain body parts of the hobbit. I don't condone any kind of violence towards hobbits or any other creatures or living things, whether mythical or supposedly real, but this is just a way to get you thinking about how to model things and then how to generate data from some existing data. So they give the example of the Hobbit model, and if you notice here, so we've got things like head and left eye and left ear, but there's no right eye and right ear. So what they've done is just model where there's a pair of body parts. They've just modeled the left-hand side. So if we want a full hobbit, as it were, then we'll need to at some point write a function that generates the other parts, the missing parts of the hobbit model. And this is quite useful because it's the left eye and the right eye are the same, are going to have the same properties except for the actual name, and so it's kind of more efficient to just define the basics of the model that we need and generate the rest. It's much more efficient and probably less error prone in your code. And we can see this is a vector of this is a vector, so this is like an array-like structure in Clojure. And we can also consider this as a sequence. So you can consider this as a sequence of values. and each value is just happens to be another kind of collection type. In this case, a hash map, and a hash map has keys, two keys, name and size, and the each key has a value, so it's a key value pair. And this is a fairly common way of approaching modeling in Clojure. We've got something very similar in the project I'm working on at the moment. Got a whole bunch of information, and it's just basically a vector of maps, and that way you can have like a nice sequence of values, but also each value is more specifically defined with some context, like name and size, rather than just having the left button too. It gives it a bit more contextual meaning and makes it easier for the human developer to be able to understand what's going on with this data structure. So let's jump into my code. Let's go up to the top. Yes, I did put a health and safety warning at the start. So hopefully you won't be going around hurting poor defenseless hobbits, unless your name is Sauron. So we've got this model here, and so the name's fairly obvious what it's doing. It's just naming the body part, and the size refers to how likely it is that that body part is going to be hit. Oh, well, I spelled that wrong. So if we consider that like a chest is of size 10, that's more, your chest is more likely to be hit than your left ear, for example, which is just a size 1. And so so we're going to create a function at some point to generate all the right eyes, right ears, and there's a whole bunch of other ones that are kind of left only. So we'll need to generate things for that. So I've got a REPL running already, I believe. Yes, my REPL's running. And so I can just evaluate this. And so we get the name for this collection, and we can just use that name throughout the rest of the code. And you can see it's giving it its fully qualified name here. So this is Practicalli exercise Shires Next Top Model, because that's the namespace it's in. You can see the kind of the directory structure up here, and this is a namespace, and this is the actual name of the thing that we're actually pointing at. Let's see. Yeah, so body parts is a single collection. Each element is a hash map. We've got key value pairs, and the keys are defined using keywords. Now, this is a useful thing to do. It's quite common to use keywords. So like anything that starts with a colon is a keyword in Clojure. And that has some extra properties when we use those as keys in maps that we'll see as we're defining our function. Just helps us write a slightly simplified bit of code to be able to extract things out from. So if we wanted to get something out of this map here, let's grab this map for example. We could just use get and then pass in the key, which just happens to be a keyword, and that gives us the value. And we can simplify that. So instead of using get, we could actually just use the keyword itself as a function. Oops. So there's that's the map, but we can just use name here, and name acts as a function with respect to this map. And saying basically it's the same as the get me the value that name points to. And just for completeness, we can also use the map as a function, and we can supply the key, And when we use the map as a function, then the key that we give doesn't have to be a key word for this to work. It's only when we're actually using the key as the function. Oh, that gets a bit annoying, doesn't it? There we go, sorry. It's only when we use the key as the keyword that we can use that as a function. But if we're using the map as a function, then we can pass it in. So it doesn't matter what type of thing the key is. It could be a string and so on. Okay, so if we wanted to get things out of the this model that we've created, this asynchronous body parts, we can get the first and the rest. This will be quite useful to understand later on. So we can actually get if we get the first thing from there, that's the first element of the vector that we're pulling out. So we can see we're pulling out the head first, and then we can get the rest. So we can get everything else, everything that is not the first value. And so actually using these two helps us iterate over a sequence. We can do first and rest, and then if we pass the rest back to our function, then we can go round and round, and each time we're taking the first value away and doing something with that, and then passing the rest of the values back in. And so eventually you'll go around this many times. So like where is it? So we've got 18 body parts, so we'll go around 18 times, and on the 18th time rest would return an empty vector, an empty collection. So there we would then know that we'd finished iterating through all these values. So we'll see that a little bit later when we start doing the function. And we can put this into, we can use this idea along with destructuring. So what we're doing here is we're taking the body parts that we've defined above. So this is our collection of hash maps. And we're saying get the first, so we're going to bind the first one that we pull out from there to this name first body part. So this is first body part. And so we're using the let, which basically defines local names. So it binds the, if you can't remember what let does, so we do if we do a let, we're binding a name to a value. And so in this example, we're actually using this destructuring part. So we're actually putting in the structure of the thing that we're looking at, the thing that we're trying to bind to, and saying we actually want to bind something that's inside there. So this vector that's inside the let vector is actually referring to the vector that's inside the Hobbit body parts. All right, if you remember, this is a vector of maps. So we're saying match this vector with this vector, and the first thing in the vector we want to bind to the first body part. And then using this ampersand, it says just everything else that we pass into it, we just want to bind that into the rest of parts. So this is the same as you can use inside a function definition as well, and we'll see more examples of that in further episodes. And so if we evaluate this, I'm just going to return first. There we go. What have I done wrong first there? Oh yeah, sorry. Yes, I changed that, didn't I? There we go. So yeah, so if I evaluate first, then it's going to return the first element of that. So we can see that it's taken head from the body parts, the Hobbit body parts. And if I did rest instead, rest of parts, then it's everything else. So you can see the first one there is left eye, which is the basically the the second one from the original vector. Oops, there we go. So the first one is head, and we're skipping over that one, and we're just getting left eye and everything else after that. Whoop. Yeah, so we get left eye. Yeah. So that's a nice way, that's a kind of useful way to iterate through this. So if we keep going around in the loop over, we have some kind of function that goes over our collection, then we can get the first, do something with it, and then pass back the rest, and so on and so on. And that's a very common pattern. And when we iterate something, we want to actually do something to actually generate the rest of the body parts. So we've got all the left body parts, and we want to generate the right ones. So we've written a little function that we're going to call within our iteration of the collection. And it's going to take a part name. So it's going to take basically a map of name and size. It's going to take that. Oops, I want to do that, sorry. And then it's going to take the name. Well, it's going to return a map. So it's going to take a part, which is a map, a hash map of name and size, and it's going to return a map of name and size. And the value for name is we're going to take the existing name from the map that we passed. So again, we're using the keyword here to pull out the value for name from part that we passed in as an argument. And so that is going to be, if it was, so the first one is going to be head, and then the next one is going to be eye and leg, and so on and so on. And then it's going to use this function called replace, and say replace in this string that we get from name, replace where we see left. Oops. If there's a left string in here, then replace it with right. So if there's a left eye, then we're going to get a right eye in return. And we're using this little hash string here, and this is the literal syntax for a regular expression. And so this is just pattern matching. So it's going to match on a string that starts with left. And the little caret here basically specifies that this part of the pattern has to match from the beginning of the string. So if that was so if we had like first left, it wouldn't match. But if we have left ear, then it would match. And it's going to substitute where it finds left with right. And then for the size, it's just simply returning back the size, the original size of the part. So there's no difference between the size of the left eye and the right eye. Yeah, and there's just some details there as well. And we can also use this refind to check our regular expressions are actually working just by themselves. So here we can see that we've got this pattern defined, and we want to find that inside this string to see if the string contains it. And if it does, it's going to return that string. And if it does not, then it returns nil. I think I've done a video on regular expressions. I'll dig that out as well. But they're very useful, and there's some nice on exorcism.io. There's some nice examples I've got of using regular expressions to simplify things. And so if we call this matching parts with some example data, so again we're only passing in the part, so that's like each element of the overall vector that defines our hobbit. So we've got a matching part here that we're calling this function with this hash map. And so this is a left eye, so this should return, hopefully, a right eye, which it does. and it's of the same size because that's what we asked for. If we get a head, then it's actually just returning head. It doesn't find a left, so it can't substitute in the right. So it's just returning the original value of head in there. There's no substitution going on inside here. And then yes, so that's the function we're going to call during our iteration. As we're iterating over the entire collection of body parts, we're going to call this, and it's going to either return the right equivalent of that, or it's going to return exactly the same unchanged. So let's have a look at the iteration. So we've got this symmetrized body parts function with a docstring, which is nice. So that's, that pops up in my little docstring shower up there in the top corner. And we're using, we're defining an argument to this function called asym body parts. So this is the collection of Hobbit body parts we're going to pass in. And we're using quite a low level kind of abstraction to iterate over this to start with. The advantage of this is we can see exactly what it's doing, and you can have like very specific control over what your iteration is doing. The disadvantage of this is you have to write everything yourself, and it's not using some of the really nice abstractions inside Clojure core, but we'll come and use some of those to show you how to make that a nicer and kind of easier code to work with. But let's start with the loop to start with. So a loop is a bit like a function call. It's going to allow us to iterate through a collection by essentially just returning to the loop each time. So we've got this loop recur part of the code. Oops, what did I do there? Oops, sorry, bunch of fingers. And so the loop is taking some arguments, and this is like it's a bit like a binding function, like we do with the let. So it's basically saying we're going to define this local name called remaining asynchronous parts, and we're going to bind that to this asynchronous body parts. So that's the argument that we've passed in. And the other argument to loop, the other binding that we're doing is this final body parts. And we're setting this to an empty vector. So this is a vector that's going to contain all our generated body parts and all the kind of the existing ones that are there as well. So this is going to create our complete Hobbit, our total Hobbit. And we're going to check. As we go around the loop, we're going to check to see whether this remaining asynchronous parts has become empty. And if it's empty, then that's because we've got to the end of the Hobbit body parts, the original set of Hobbit body parts. And we'll just return the final body parts because we should have everything by then. If we still have values in the asynchronous remaining body parts, then we're going to do this other. So this is if. So this is in this if statement. This is the true expression. It's just returning that value, and the false expression is the let recur. So we're basically going to use the let to do this destructuring that we've seen before. So basically just pulling out the first element of the vector. So we're pulling out the first map in our collection, our sequence of body parts, and then we're also pulling out the remaining. So now we've got the first one and the rest of them. And then this is from this remaining asynchronous body parts. And this value is the value that's getting changed each time we call loop. So this value is going to decrease each time. So the first part that we pull off is going to be incrementally kind of closer to the end each time. And then the recur is calling back the loop with the remaining. So this is the rest of the body parts. And then we generate, or we add basically to the final body parts. And this is where we're calling this matching part. So we're calling the matching part with the part. And then the result of that is either going to be something like head, or it's going to be right eye. And then if it's head, it's going to be the same as the original part value. So we're only going to we use set to basically say, well, we only want one. If both of the maps are the same, we only want one of them. So we don't want two heads. We only want one head. And so this set will make sure that we only get one, and then I'll put that into the final body part. And so into is just basically saying I want to place a value into a data structure, and in this case the data structure is represented by the final body parts. If you didn't understand that, that's fine, because it's quite a lot there. One of the tricks I use to understand things like loop recur is in Cider there's a nice little debugger that allows you to step through everything. So we're going to do that. So we're going to put a debugger on this. So this is $db and spacemax, but it's basically the Cider debug function. So this puts in a bunch of breakpoints, and you can see the name is highlighted with a square red. And now if I call this expression, if I call this function with the body parts, then we can step through and we can see what it's actually doing. So this is our Hobbit's body parts. So this is the same. We haven't changed this yet. We're just assigning this to the remaining body parts. And then we get we check to see whether it's empty, and because remaining, we've only just started, so it's not going to be empty. We've still got everything in there. So this is false. So then we skip over that final body parts and go into the let. And now we can see we're actually starting to, we're going to start dividing in the remaining. So the remaining is everything but the first element of the original vector. So we've lost the head, and we're only going to return the left eye onwards. And then the final body part, initially it's empty. It's an empty vector because we haven't added anything yet. So we're going to put into that whatever we get back from the matching parts. And so we've got the part originally, which is a head. And so we're going to pass that in. Oh, I'm losing my voice. So going to pass that into matching parts. And this is returned head, and because we're using a set, then we're only going to get one value of that, because we're using set, it has to be unique. So when we run the set function over something, then it's kind of reducing, it's making sure that there's only one of every unique value there. So basically it's just dropping the new head and just using the original head. So that's what was going to get put into the final body parts. And then we're just going to go round and round here, just around the loop, just to see whether this is empty or not. And so now we're passing the left eye, we get a right eye. And because left eye and right eye are different values in the set, then we're going to pass both of those into the final body parts. So we've got our head, left eye, right eye, and we go round and round. So we now are on left ear, and we can go round, as many times as we want. And we'll be here till Christmas if I do that manually. There we go. And so when we've gone around the whole thing, we go around and we can see we've got, oops, Let's just take the debugging off. Now we've got left eye, right eye, left ear, right ear, and so on and so on. So we've generated all these extra parts that we needed for our body. There's no questions so far. Yeah, so this into is basically, we can see here, there's just examples of, if it's a set and we've got head twice, then it's just going to put head into it once because it's a set. But because these values are different, then it keeps both of those values in the set, so that puts that into the square bracket, into the vector. Oh yes, you could do this without the let. So we could use the first function and the rest function. The slight advantage of the let is we're using this first remaining parts twice. So this does kind of so the let does remove some of the duplication, and using the let with the destructuring is slightly nicer as well. But this does exactly the same. So if I call it, I get exactly the same results there. So if you do this approach, this is fine. Although you might realize when you got two of these first remaining async parts, that you can put those into the let, and then you might think, okay, yeah, then I can do destructuring to just make that slightly simpler as well. But essentially, it's doing the same thing. We're getting the rest. We're sending the rest here, and we're just using the first element when we're generating a new body part. Going loopy, no questions, no. Yeah, so we kind of toured through loop there with an example. They include some other examples here. Of using this iteration. So here we're just basically binding iteration to 0. And then if the iteration is greater than 3, then we're going to say goodbye. And we're just recurring by sending the value of iteration back. So iteration was 0. We increment it, so it's going to be 1, and it's going to go around the loop and loop and loop until this condition is true, and then we print out goodbye. So that's why it's doing 0, 1, 2, 3, 4, and then goodbye. So loop is quite it's quite simple, but tends to be quite verbose way of doing things. So there are some nice abstractions around it. They do show an example of using a recursive function as well. There's not a huge amount of improvement there. This is doing the same kind of thing. So here we're just printing out the same kind of stuff. So we're printing out iteration and then goodbye. And so this is kind of similar. We've got the function defined around it, so we give it a name. And we've got two different kind of branches, so we can either recur with with no arguments. It will start. It's just basically starting there. It's going to call itself with the value 0. And if we're passing in a value, then it's going to start that iteration point. So we can either call this recursive printer, or we can call it recursive printer 2. And if we do that, if we do this, then we get 4. If we do this, we get less than 4, because we're starting at a higher value. So we're skipping the 0 and 1. But essentially what it's doing is it's doing the same thing as a loop. Essentially the function name is the loop, and so the new value of iteration is going to be passed in by calling itself. So recursive printer calls recursive printer, but this time we're calling it with a different value. So this is kind of updating what iteration is. It's going to go through the iteration. So it's working exactly the same as loop, except it's kind of like it's named. The disadvantage of this is that it's going to use a little bit more memory because it's basically calling a new recursive printer function each time, whereas loop will just use the same piece of memory. I'm just going to close this window. So what you can do instead of calling it using its name, you can also use recur in there as well. So this makes it as memory efficient as, well, almost as memory efficient as loop, because we're using recur. So that's going to reuse the same piece of memory that you used for the first iteration. It's going to use the same bit of memory for the second iteration and third and fourth and so on. So the only thing to be aware of is that recur, this has to be in the last, so this has to be the last thing you do in a particular branch. So here in the if statement, if it's false, then the recur is the last thing we do. We can't have any more expressions after the recur or it won't work. But this does exactly the same thing and just recursively prints that as well. Except it's just slightly more memory efficient than calling by name. So kind of the abstraction levels you go through, it's quite common when you're first starting to start with loop, because especially if you're familiar with iterative incremental iterative programming, so basically you do step by step by step by step. If you're used to doing that, then loop recur is sometimes a little bit easier to reason with. And if you can't use a higher abstraction for some reason, if it doesn't quite do what you want, either you need to go and think about the problem a bit more, or just use loop recur until you figure out how to make it kind of slightly nicer. There's nothing wrong with using loop recur, but there's usually a nicer abstraction to use. So loop recur or a recursive function, it's just slightly higher abstraction. And then and then you've got like the Clojure core functions like reduce and reducing functions, which are a really nice abstraction over this, and typically the way that we approach things. And slightly more advanced on top of that is this idea of transducers, especially when you're dealing with collections that you want to define a kind of pipeline of transformations on top of that. So it's kind of like an extension reduce for lots of different cases. So rather than doing loop recur, we can do reduce. Oh. There's a question in the audience: will this get into a 5 or n appendage part? I'm not quite sure I understand the question. Sorry. No, I don't understand the question. If you want to try and rephrase it, I'll try and think about it. But essentially, it's because we've got this if statement. It's always going to, I guess, if you get the condition not quite right, you could kind of never end and go on to an never-ending increment. That is always possible with loop recur and recursive functions. If you get your terminating condition not quite right, you might have to abort your REPL, interrupt the expression you're evaluating. This is a fairly simple condition, so I don't think anything can go wrong with that. It's basically just, is it greater than 3? You might put the less than by mistake in there, and then it would go on forever. But yeah, if you get the condition right, you shouldn't have any problems. And if you do, that's what the debugger is for. So reduce. Let's look at reduce. I've been skirting around this. This is where the good stuff is. So there's some simple examples here that they cover. So just reducing our collection by using a function. So this function is basically going to take each value and add them all up. Essentially, that's what it's doing. So we can think of this. What reduce really does is it takes the first two values and it's going to create an expression using the function to add them together. So we get this nested expression here, and then it's going to take the next value and make that. Oops. So you're going to get that, and then it's going to take the next value, and we get the plus 3 plus that result, and then the next value we do 4. So what we can do is we can actually just show this how Clojure would actually evaluate this. So come in and I mean it's fairly obvious what this is doing, but if you weren't quite sure, if this is a more complex one, then you could actually just use the val with replace value. So I'm going to do $EW in spacemax, which is cider eval last s expression and replace. So it's basically evaluating this nested expression. It's going to replace it with its value. Oops, did I not do that right? Oh, I have to put it there. There we go. Yeah. So that's 1 plus 2 is 3, and then we're going to evaluate the result of that expression, which is 6, and then it's going to add that to 4, and then we get the result that we want, which should have been 10. Oops, I don't know what I did then. Oops, which is 10. So that's basically how reduce is working. It's taking it's taking two values, using the function with them, and then using the function with the result of that with all the other elements in the collection. There we go. And if there's a value, because you can provide an initial value, an initializer, and this can be a simple value, or it could be some kind of function that generates a value. And so here we've got 15. So rather than taking the first two elements of here, it just takes the first element because we've already got a number already to add to it. So then it's just putting that inside 2, 3, and 4, and it does the same thing. I'll come back to your question after recur. So let's see. Yes. So reduce. So we got that's the basics of reduce. So how are we actually applying that to our body parts generator? So we're still taking in the same body parts, and this time we're doing reduce with our own function, and we're going to also pass in a value, and this value is going to be the empty vector, and then our collection is the body parts. So rather than just using a simple plus function, we've got our own anonymous function here. So this is taking final body parts and part, and it's basically just generating. It's doing what we were doing before. It's doing the generating the matching part, putting it into a set, and then so it makes it unique, and then it puts it into final body parts, and that's that we get the same results as we would do with the body parts. So here we're still getting left eye, right eye, and so on and so on. I'm not sure if the debugger shows this as much. Yeah, so those are our body parts, and so we've got to start off with an empty final body parts. We take the part, so that's the first part, the first element in the collection, and we generate matching parts, which is returning a head as well. That's the same. So we've got a set. So we just put that into the body parts. So that's our first iteration, and then the next iteration we get the next part, and so on and so on and so on. So the reduce is basically responsible for grabbing out the individual elements and giving them to the anonymous function as we go through. So it's giving them this final body parts, which is this empty vector, and the part, which is the individual elements from these body parts. And yeah, and then it's going to keep on going and going and going. And gives us the same answers. And just one refinement on that you can do is you could extract. So where we've got this anonymous function in here, you could extract that into its own function, especially if it was complex, or if you were going to share it, or if it had other uses throughout the code base. And this function is your reducing function that you're using. Basically, a reducing function is a function you use with reduce. So we've got this generate body part, which is taking the final body parts, which is and the part itself, and it's just putting them into there as normal. And this simplifies our reduce a little bit as well. So it kind of separates out the iteration from what it's doing on each iteration. There's not much difference between those two, I don't think. There's probably not much merit in this example to extract that because it's fairly simple. But it's just an example of what you could do potentially. Especially if you've got a really long reduce in here, you can kind of separate those functions out. And if you've got if you've got a really big anonymous function inside here, then it kind of suggests that you might want to do a bit of refactoring or rethinking around that. What else was I going to do? Oh, and then there's hit. Let's look at that question. So Headflax is asking, as opposed to left and right being stuck on the there's no problem asking questions. I'm just not quite sure what it is you're having problems with. If I can't solve it during the broadcast, feel free to have a chat with me on any of the Slack, Discord, or Zulip channels, and maybe sharing some examples of the code you're stuck on there will be quite helpful to me to understand what you're trying to do. Oh, so you want to add more appendages? Okay, I'll have a think about that. Yeah, the appendage thing is quite simple. If you had more than one hand, it's like more than one pair of stuff, then I don't think this is really doing that. We would need to kind of do something that generates something more interesting with when you're taking the body parts. I guess, yeah, because we're only replacing left with right to get a right one, but then we're keeping both because they're the same. I think if you wanted to generate 3 arms or 4 arms or 5 arms, then that would be, you'd have to rewrite how you generate the arms. So you basically have to rewrite the matching parts thing there. And as long as you're returning unique values, so if you have, you could have like left eye, right eye, and center eye. All you would really need to do is just change how matching parts works. So instead of just doing replace, you'd have to kind of generate like all the different combinations you wanted to, and so long as they're in the same kind of form of a map with a name and a size, then with different values for the names, then I think the rest of the code would work just fine. You just need to figure out how to kind of do the matching parts aspect. That's an interesting one to think about. That's an interesting homework one. More than 2 body parts. I think that's what you're asking. Feel free to correct me if that's not the case. And then the last one, the last part. There we go. This is a curious one. So I think to wrap it up, we have this example where we're trying to determine if a body part has been hit. This doesn't feel entirely scientific, but it is another useful example of kind of looking at loop and recur. In this case, we're going back to loop and recur again. So we've got this loop recur section. So what we're trying to do here is we've got our parts. So these are the parts that we generate. So we're generating the complete set of parts from our like partial set of parts and binding that to sim parts. Then we've got body parts size sum. So we're adding up the sum of all the body parts, and then we're going to define a target, which is going to do a random body part size sum. So it is generating from this line above, we're defining the total number of the total value of all the body part sizes, and we're just generating a number within that value. So like I think is that 0 to that number. All right, there we go. So it returns a random float number between 0 and the whatever we pass. By default it'll be, so if we didn't pass a value, it'd be 1, so it would do a value from 0 to 0.9999999 because it's exclusive. So that means it doesn't count the last number. Okay, and then we loop, we do our destructuring again of the body parts. So we get the first and last, so we can kind of iterate again through all of the body parts as we need. And it's got this accumulated size that it's building up. So it's basically pulling out the size value from each part, or from the part that we give it. And then it's, so this will be the first part it does, and then the next time around it'll be the second part we get. And then we've got our check to see whether we need to finish recurring. And so we're just saying if the accumulated size that we're generating is bigger than the target. So the target that we've come up with, the random number. So this randomly is going to randomly going to chuck out a body part based on the random value we get here, plus our iteration through until we get enough body parts to be bigger than this size. Which is, yes, I'm not quite sure I would take this approach, but it's interesting. It's an interesting way of doing generating a random body part. So let's just look at this, the debugger. I think that's a little bit easier to see. So passing in all the body parts, and then we're generating all of them. So we've got left eye, right eye as well. And all the body parts, if we take, so here we're doing a map, so it's like it's iterating like reduce and like loop recur. It's iterating a function. In this case, we're using the keyword size as a function. So over each part, we want to get the size value, and map returns that as a sequence of values. So these are all the values from each body part, and then we're going to use reduce to add them all up and get a total value of 85. So that's the sum of every single size value in our body parts, in our full set of body parts. And then we're going to take that body part as the maximum, so we can't generate a size bigger than that, a random target bigger than that. It has to be less than 70, less than 85, and we got 17.5. I'm sure we could probably use rand int, but there we go. Never mind. And then we're going to iterate round here and just get basically get the size of each part as we iterate round, and then that becomes the accumulated size, and then we check to see whether that's bigger than the target, which it's not in this case, and then we just recur. And this time we've lost the head, and we go round and round and round and round. Let's see. Oh yeah, let me just sneaky. Let's shortcut this. So let's put that 17. So I'm just going to inject this value in there, so that the accumulated size is now 17, and we're getting closer to our target. Nearly there. One more time round. So the next value it's going to get from this part should take us over to 18. Oh, yeah, just. And then that kind of meets the target, so that's going to be true, and so it's going to return the part. I think it's a useful example of using loop again. I'm not sure if this is the way I would kind of identify the body parts, because it seems very random. But yeah, there we go. Cool. So this has been a really nice example of loop recur. I think if I go to my browser, let's see, remember how to use my computer for a second. If I go to GitHub and go to Practicalli, there is a lot more examples of using loop recur, but then also showing how to write them in a more abstract way using things like reduce and other functions from Clojure core. So if you look for Clojure, and there's one example, so in source, there's one example, I think it's 53, if I remember rightly, longest increasing sub. And this is a tricky one. This is one that it doesn't really kind of, it isn't obvious how to do this in a kind of more functional approach. So I've started off basically trying to, you've got a sequence of numbers and you have to find the longest subsequence basically. So in this case, 1, 2, 3, 0, 1, 2, 3 is the longest increasing sequence without any gaps. So it does require a bit of loop recurring. So there's like a really nice long loop recur thing here, which these do work, but it's quite verbose. But it just show like a way of doing this with Clojure to kind of like start stepping through the individual pieces. And if you've got a debugger as well, it's very easy to kind of follow exactly what it's doing. So some different examples there. And then I kind of start to think about, well, how else could we do this? How else could we tackle parts of it so we can actually partition up the pieces of code? Let's make that a bit bigger. There we go. And you can add a step in it, so you can actually partition individual pieces, and then start applying like whether values are greater than, whether the previous value is greater than the next value, and so we can also partition by, so we can actually generate like different data sets and see which one of these is actually increasing in size, and if it's not, then we can actually drop them. Yeah, so we can. So here we got 3, 0. We can actually get rid of. We know we can get rid of that because 0 is less than 3. But these ones are always increasing. So 0 is greater than, so 1 is greater than 0, 2 is greater than 1, and so on and so on. And then we can start to filter out the ones that we don't want. So where the first number is less than, so yeah, we want to keep where the first number is less than the second number. So now we've lost that 3 0 element from the end of here, and we've just got those, and then we can just sort them out by the longest one, and just get the first. So we've already taken that loop, that big long loop recur, and actually just replaced it with a fairly simple kind of abstraction using partition and partition by, and a filter. And I think there is some other examples here where I've reduced it even further. I'm using concat here as well. Yeah. Yeah, I'm just using let here to kind of bind some names to kind of just show you the different steps. And then we just concat the results together. Yeah, so it kind of, these do show you kind of ways you can write the solution in loop recur if you're struggling to find the right abstractions, and then have a rethink and say, well, how can we break this down into different approaches using some of the more abstract functions in Clojure core. So there are quite a lot of those in here. I think most of them are, yes, I've got the first 60 odd of foreclosures in there. A lot of these, I think, from like the 40s onwards, I think there's a lot of examples of using loop recur as like the very basic way to do things, but then showing you the abstractions as well, which I think gives you a more complete understanding of what the abstractions are actually trying to do as well. Okay, it's past time. So if there aren't any more questions, or if you want to follow up on anything, or you want to share some code, help me look at things, feel free to reach out to me on any of these channels. If you haven't already subscribed, then please do so. I'm not quite sure how many subscribers I've got now. I think it's over 1,000. Practically, I'm curious now. 1.11 subscribers. Well, thank you very much for everybody who's done that. It's a nice little boost to see people that keep coming along and joining. And if you are using this stuff for work, or your work has some budget for sponsored open source projects, then feel free to consider my name as well. Everything I do is open source and available as Creative Commons, so anybody can use it. Okay, I'm going to leave it there. There's no more questions. I'll see you either in the chat or next week. Thank you very much, and see you next time. Bye-bye.